Hey, good morning, everybody. So we have today our last scheduled talk of the season, of the spring season. So by Maryam Taghi Zadeh, a PhD student in engineering, who's going to talk to us about XMSS, or stateful approach. Thank you very much, and so floor is yours.
Hello, everyone. My name is Maryam. Welcome to my talk. Today, I will be talking about XMSS. I will be talking about hash-based digital signature schemes, focusing on XMSS. XMSS stands for Extended Merkle Signature Scheme. And it is an important topic in the post-quantum cryptography. Let me start with the key advantages of XMSS. Unlike traditional signature schemes that rely on mathematical problems, XMSS relies purely on hash functions. It also offers compact signature, strong security. Even if the collision resistance is broken, it uses Voigt's construction as its base, and then try to create the related tree on top of the Voigts. So, what's digital signature scheme? Digital signature schemes work using public-private key pairs. The private key stays secret with the sender to create signature, but the public key is shared with everyone to verify if the message is integrated or no. This system verifies both who sent the message and that it hasn't been changed during sending it. The first key property of the digital signature scheme is authenticity. This answers the question, who signed the message? A valid signature proves the message came from someone who has the matching private key, not an imposter. Only the rightful signer can create valid signature. The second key property is integrity, which answers, has the message been altered? Even a tiny change to the message invalidates the signature. This works because the hash of the original message is encrypted with a secret key, sender's private key. If anything changes, the verification will fail. So, since the XMSS is built using hash function, and hash functions are the main component of hash-based signature digital signature schemes. I'm going to have an overview of hash function to see what's hash function doing, and also I have a brief look at the 12 most important and widely used hash functions in SHA-2 and SHA-3. As As you can see here in this table, we try to create hash of hello world with SHA-256, and then try to change the first character to the uppercase. And as you can see here, the hash value will be completely changed. And also, SHA-2 result will create a completely different, hash digest for the same input message, and SHA-3 will create a completely different. Hash functions create fixed size fingerprints of data. As I mentioned before, notice how completely different outputs are generated when inputs differ by just one character. You can see it. The avalanche effect means a small input changes causes a dramatically output change. The functions are one way, and this is the specific specification of the hash function. You can't reverse the function at all. As you can see, hash functions are used in several applications. The most important applications are signature generation, signature verification, key derivation, MAC, and random number generation. There are several important hash algorithms like MD5, SHA-2, SHA-3, Blake, but MD5 and SHA-1 have been broken because researchers found some collision attacks against these two hash functions. SHA-2 is similar to SHA-1. It uses Domgard, Domgard and structure, but the SHA-3 uses a completely different structure. It uses sponge construction. Now let's take a brief look at SHA-2. SHA-2 family, as you can see, including SHA-2 224, SHA-256, SHA-384, SHA-512, and the output size of the digest value it depends on the value, the suffix after this dash. As you can see, like SHA-256 will create outputs 256 output bits with using word size of 32 bits, and it uses 64 rounds, while SHA-512 uses 80 rounds with 64-bit words. And the process of SHA-2 involves padding the message to a specific block size, parsing it into blocks, and then performing many rounds of compression. Let's have a look at SHA-2 256 block diagram. So, as you can see here, the message, the original message comes into SHA-2, and then it is padded to make sure it is multiple of 512 bits by adding 1 and concatenating, some zeros, bunch of zeros in the last block. And then we just choose one 512 bit, which is created from 1632. Let me zoom in. 1632 bits, and then try to expand it via giving it to the message schedule function here to expand it to 64 words of each word. It has 32 bits, and then we will give each of these words to a separate significant round of the compression function. Here in the compression function, we also have we also have inside each round, we also have these 4 main functions: CH, sigma 0, sigma 1, and majority. And the final result in our function will be our 256 message digest. Now, let's take a brief look at SHA-3. SHA-3 is based on Keccak algorithm. Keccak was the winner of this competition. Unlike SHA-2, SHA-3 uses sponge construction. The family of SHA-3 includes are including SHA-224 through SHA-512, but also in these 4 members, we have to have a fixed input message size. But SHA-3 has also 2 extendable output function, which means that you can give a shake, named shake. You can give shake arbitrary size of input, and you can get arbitrary size of output as your digest value. So, as you can see here, for example, SHA-3 256 will produce 256 output, while the rate bits are 1088 bits, and the capacity has 512 bits. Keep in your mind that the rate bit should be equal to the message block size. And Keccak algorithm has 2 main parameters, named B, and B represents a fixed length of a string, but in SHA-3 we have to use 1600 bits as our B, and the number of rounds in SHA-3 will be 24 rounds, and each round contains 5 step mappings function. Keccak works on a 3D array, as you can see here. For SHA-3, we use a 1600 bit state represent as a 5 to 5 to 64 array. We convert back and forth between a linear string and this 3D array string processing. When we get a string, we have to, before starting the SHA-3 process, we have to convert it to a 3D state array, and then at the end of the process, we will convert back the 3D array to string. Why this 3D array? This structure helps achieve the strong diffusion properties, which we need in the cryptography. Let's have a look at SHA-3 256 block diagram. As you can see here, the message, the original message is given to the SHA-3. It should be padded at first and then parsed. Why it should be padded? Because it should be, as I said before, it should be, for example, the multiple of 1088 blocks to give each rate. And then we parse it to 1088 bits blocks, and each block is going to be given to a rate to be XORed with the rate. And at the very beginning of the process, our state array, this array, will be initialized by all zeros. And the first rate will be all zero, and then will be XORed with the first block of the message, and then it will be given to the function to do 5-step mappings. Inside it, it will be repeated for 24 rounds inside this function. It means that in each round, we have to repeat these 5-step mappings. And then we will extract our desired hash function, hash digest from the rate, while the capacity of the SHA-3 will be untouched, just for making sure the security of the SHA-3. As you can see here, SHA-3 has two main steps: absorbing and squeezing. Absorbing, as I mentioned before, consists of giving our original message to a function and applying 5-step mappings on them, and the squeezing step is related to getting the output from the last state. So the step mappings are including 5 steps. I just want to have a quick look at these parts. Theta provides diffusion by XORing bits across each columns. Row rotates bits within lanes according to this offset table. Pi rearranges lanes. Chi, which is the only nonlinear part of the SHA-3 function, it adds nonlinearity through bitwise operations. And iota breaks symmetry by adding round constants. So let's have a comparison between SHA-2 and SHA-3 right now. While SHA-2 uses the Merkle Damgard construction, SHA-3 uses the sponge construction. SHA-2 is generally faster in software, but SHA-3 performs better performance in hardware. And also can create the desired length of output by using its shape. By explaining our hash functions, now we can start hash-based digital signatures. Hash-based signatures use the hash functions. Since hash-based signatures use hash functions as their security foundation. So the signer hashes the original message at first, and then try to sign it with their private key. As you can see, the signer Alice has her private and public key. She will sign the original message and the hash message digest using her private key, and try to send it to the verifier Bob, while sending also her public key as well to Bob. Bob will receive the package including original message and including a message and a hash message digest. But to make sure this message is completely equal to the main message, Bob is going to hash this message and then try to unpack, try to decrypt the package with the sender's public key, and then after that he will compare these two messages to see if they are equal or no. If they are equal, Bob sends verification to Alice, and he will kind of make sure that Alice is the main sender. The authenticity of Alice will be proven, and also Bob will verify that the original message didn't alter during the sending process. There are two main types of hash-based signatures: one-time signatures and many-time signatures. One-time signatures schemes can only sign exactly one message per key pair. It means that when we use a key pair, we are not allowed to reuse it at all for signing any other messages. Many-time signatures can reuse key pairs for multiple signatures, but with the security risk will be arise. But both approaches were first proposed by Merkle in 1979. So, post-quantum signature schemes comes in several variants. As you can see, we have hash-based signatures like XMSS, LMS, and Sphinx, while we can also have lattice-based signatures like Dilithium, Falcon, and other multivariant polynomial schemes. Now we are focusing on XMSS, which is a stateful-based scheme. but LMS and XMSS both are a stateful scheme, but Sphinx is a stateless scheme. But what does stateful mean? A key concept in XMSS is that it is stateful. This means that the private key changes each time you sign a message. If you reuse the same key, the security breaks down completely. This requires a careful tracking of the key's state. So we will have introduce some index for each key to track them to make sure if they are used several times or just once. Okay. At the very beginning of the process of signing, we have to take a digest message from the original message. We use this message digest to convert it to a base W, or also we can use this message digest to compute the checksum and then convert the checksum to base W. I will explain why we will use checksum during the message digest. But before that, let's talk about what's parameter. What's stands for Winternitz one-time signatures, and because it provides the faster signing process, we will use votes in our XMSS as our base. It means that our XMSS will be constructed on top of the votes. But at first, before starting XMSS, we have to create votes structure. Votes has two key parameters, n, the message digest length, and the Winternitz parameter. Winternitz can be chosen between 4 or 16, just 4 or 16. And with choosing the Winter parameters, we can choose that the signature size is going to be large or no, and if we choose the higher W, we will have the higher, larger signature size, while the speed of signing is the lowest. We will derive 3 other values from these key parameters, named len1, len2, and len. len1 processes the message, while len2 processes the checksum, and as I said before, W16 shorter signature and slower signing. So I mentioned before that our message digest should be converted to base W. But before that, we should create a checksum for the message digest. Let's see if a message digest without checksum is used during the process. The attacker can increase some values and decrease some other values, and he can keep the balance of the addition of the these values. And when but when in the message digest we use the checksum, the attacker cannot cannot make any changes during the message digest value. As I said before, WOTS is an improved version of OTS, which use Winternitz parameters to control the signature size and speed. Okay. WOTS uses two main functions as core functions: a keyed hash function for chain computation and a pseudo-random function for key generation. During the process, we will deal with these two main functions a lot. And the XMSS, after that, XMSS randomizes the hash calls by adding both a unique key and a bit mask to that XOR with the input. It means that we will use, before hashing, we have to XOR the message, the original message, XOR with the bit mask. This bit mask is unique and randomly chosen, and after that the result will be given with the key, with a unique key which is produced by this pseudo-random function given to the hash function, and then create a randomized hash message digest. But it differs from the normal hash function, which we give the original message to the hash function to get the output. And in the randomization of hash function in XMSS, we will have a unique key and unique bit mask alongside with the message to prevent the attacker to guess some random value. But in the normal hash function, the attacker can find a pattern during the process and guess the value. That's what I mentioned here. So let's talk about chaining function in the WOTS process. The chaining function is central to WOTS. It takes an input. I will explain it more. It takes an input as a starting position and the number of iteration, and also it will create a bitmask generation. Bitmask with a pseudo-random function, and then will XOR together, and the result will be given to a hash function aligned with a unique key that is generated with a pseudo-random function, and after that we will have a keyed message digest, and we will give it to the next chain. So let me show you the picture at first. This is the chain function of the WOTS. As you can see here, our message, original message, is given to the hash function. We said that we will create our message digest, and we will concatenate the checksum to it, and the checksum length is len2, and the message digest length will be len1. And this is hash function named hash message function. And after that, we will have some bit values. And for example, in the first bit, we have 1. It indicates that in the chain, during the signing process, in the chain of words, we will stop after doing the first hash. For example, the second value will be 7. It means that the second hash chain will be stopped after doing 7th hash function, and so on. For example, if we have A in the last bit of our message digest, it means that we will stop after hash number 10, and we will use the rest of these hash functions later on in the verification process. But it was for signing process. But before signing, we should have we should create key pairs in the words. In words, we will use some. Let me. Since I shows the words with the, XMSS, within the XMSS structure, I have to explain words it at first and then continue it. At first, our message is given to the pseudorandom function named hash message, as I mentioned before, and then add the checksum to it, and then after that we will create some private keys from these random seed. We can create all private keys together at the same time, but it's the naive method. But in the optimized method, we will just we will create a private key on demand when we have having just some random seed. And when we create the private key, we will have, we will determine how many chains in this private key can be used. As I mentioned before, it is, I took an example, it is 67. It came from here, 67. Is the addition of 60 for the length of the message digest and the 3 bits of the checksum. We will have 67. It means that we have to have 67 chains inside each private key in XMSS. So after starting the chain function, at the very beginning, from starting point, we have a private key, and for as a result, we will have the public key. And the length of the chain should be W minus 1. For the key generation process, we have to complete this chain to the end to get the public keys. These are words public keys. But for the signing process, we have to stop at some point, depending on, as I said before, depending on this value. And so I mentioned it is more efficient that generate the private keys pseudo-randomly, because with just having a master seed, it will reduces the storage on hardware to store the private key. So for the verification process, we said that we will continue the rest of the hash function to get the temporary public key. It means that in the signing, we start from 0, and we will proceed until the stop value, which determined here. And then for the verification process, we will continue starting from the signature and continue all the way to the end to get the hash value. And in the verification process, I will explain it later. We will compare this hash value, this public key with the main public key root given by the standard. Okay. Let's talk about XMSS. XMSS numbers the votes key pairs according to their position in the tree. And as I mentioned before, XMSS is built on top of the votes key pair, and it uses bit masks in tree construction to prevent attackers from controlling intermediate values. And in the verification process, XMSS will use authentication path. We have, during the XMSS process, we have 4 kinds of hash function. The F function is kind of hash function which is used during the hash chain function, and the H function, the hash function which is used on top of after the votes key pair, public key pair, and during the tree, I mean L3 and Merkle tree, we will use H function. And a hash function H message will be used at the very beginning of the process when we try to convert our original message arbitrary with arbitrary length to a fixed size of a message digest. And a pseudo-random function which will be used during the hash chain. So, as you can see here, the hash function H, as I mentioned here, is not going to be used just with concatenating 2 children. We have to XOR it with a bit mask, a unique bit mask, which is created by the pseudo-random function, and it is a random bit mask value, and then give it to the hash function along with a unique key. And XMSS stateful nature means that each signature uses 1 votes key pair, and the private key tracks which one to use next. Instead of storing all possible votes private key, we store a master seed and derive key on demand. As I mentioned before, unlike the naive implementation, which we used to create all private keys and then use all of them during the process. In the optimized implementation, with having just a master seed, we will use each private key on demand. Okay. The XMSS builds its tree from bottom up. It means that at first the children is created and then parent nodes are created by concatenating two children to and then XORing it with a bit mask. I already explained them. And these are, I can skip this specification of each hash function. For example, the F function during the chain process will take n byte key and n byte input and returns n byte output, while the pseudorandom function will take n byte key and 32 byte address and returns n byte pseudorandom output. The H function during our tree, I mean L tree and hash tree, Merkle tree, we will take n byte key and 2 n byte inputs and returns n byte string. And in the H message, we will take 3 n byte key and an arbitrary length of a message, original message. So I mentioned it before. We will use pseudorandom function twice, and during the each process, during the XMSS process, while we are going to create our bit mask to XOR with the main value, main input, and when we are going to create a key, a unique key during the hash function. And XMSS parameters, you remember that votes parameter was WN, and we have also for XMSS we have also H, which determine the number of leaves, the number of private keys which is used during the process, and uppercase SK, PK, C represent the XMSS specification, while the lowercase SK, PK, C represent the votes specifications. So let's see what will happen inside the key generation inside the XMSS. So I told you that we create our private key from this part. This part is our votes construction. Okay, we will create our private keys. The private keys number will be 2 to the power of H. H is the level of the Merkle and the hash trees we will use later on. And after that, we will give them each private key to a chain function, as I mentioned before, to create our public keys. These public keys are long and cannot be used inside the XMSS process. So after that, we will give these public keys to L3 to compress them, the value, the length, and have some, fixed length values. And after that, these fixed length values create our leaves, and then each two leaves creates their parents, and from this level, after creating the leaves to the root value, we have to count a step 1, 2, 3 step. So we will have H3. It means that the height of our XMSS tree will be 3. And after that, after L3, we will create the Merkle tree. In the Merkle tree, we have to concatenate each two children together, to at the end of the process to get the root value as our public value, public key value. And then we are going to send this value, to share this value with the verifier. It was the key generation process. And let's see the XMSS private key, parameters. The XMSS private key creates from all votes private keys, leaf index, and pseudorandom function, root nodes, and public seed. These are, this creates the XMSS private keys. And I already mentioned the 3-hash algorithm. Okay, the root that I told you before, this root creates from a starting leaf index and target height. And let's start XMSS key generation. In key generation, as I mentioned before, we will have XMSS public key and XMSS private key. In XMSS public key, we have some identifier, root of the tree, and seed. While in the XMSS private key, we will have all of these values concatenated with the index, votes private key, and pseudorandom function key, unique key. But in the signature of XMSS, we will have the index of the votes key that used, as you know, as I mentioned before, in the signing process of XMSS, we will sign the original message with votes private key, not votes XMSS private key. We will use votes private key. So in the XMSS signature, we have the index of that votes private key that used, and random value for message hashing, and votes signature and authentication path is going to share with the verifier. And at the verifier side, he will, the verifier will double check the authentication path to see if the message is comes from the index votes key value. And authentication path provides the sibling nodes needed to reconstruct the root. What will happen inside the XMSS signature process? It creates a randomized message digest, and then signature generation. It creates the random. Okay. and sign it with the votes private key, and then compute the authentication path and update the private key index. While the XMSS verification process recreates in this process we recreate the randomized message, compute the votes public key, and derive the corresponding leaf, and reconstruct the alternative route, and then compare the alternative route with the shared route. It was the XMSS process, and it covered the fundamental of hash functions and how they're used in XMSS. Thank you. Oh, I used the FIPS 180, FIPS 202, and RFC 8391 during this presentation. Thank you.
Okay. So, okay, so I guess we have to take the questions offline. So, thank you everybody for attending. So we have a
Thank you.
yes, thank you. And so this was the last talk of the season. So see you in fall 2025. Bye bye.
All right. Thanks.